Here's help with the second practice test. So this question says X consists of a rigid container, so it has a fixed volume. That means the volume is constant, with 8 particles inside. When you see these particles, think of them as moles. So there are going to be 8 moles of gas in the left container X, and the right container, or what container Y, is going to have 4 moles of gas. What happens to the pressure of the system when X is converted to the representation Y at constant temperature? So you have to think about the ideal gas law, which are the variables that are going to change. So P, V, N, R, and T. In reality, P is pressure, V is volume, those are going to be able to vary. N is moles, that can vary. R is the gas constant, that will not vary, that's why it's a constant. And then T is temperature, which can vary. But in this situation, not everything is varying. So if it's not mentioned, or if it says it's constant, you assume that it's going to be constant. So the way that you can represent this is you have P1, V1, N1, R, and T1. Those are going to be the initial conditions, which all relate to X, by the way. So that's like the initial condition, all those ones. And you can divide them by the final conditions. P2, V2 equals N2, R, T2. And then, of course, you cross out things that are constant. The problem says that there's a fixed volume. So volume is actually not going to be a variable, it's a constant, so it's not going to appear. It cancels itself out. The number of moles of gas clearly changes. R is a constant, so we can cross that out as well. And it says that there is a constant temperature, so that's a constant too. So what you really have is the relationship between pressure and number of moles of gas. So you can whittle this equation down and you get this. P1 over P2 is equal to N1 over N2. Now you may see the equation in this format, or if you want to put all the 1's and 2's on the other side, you can do that as well. If you do that, then you get P1 over N1 is equal to P2 over N2. No matter how you choose to represent it, all you have to do is recognize that there is a direct relationship, a directly proportional relationship between pressure and moles of gas. Pressure and moles of gas are directly proportional using that symbol, which means that when the moles of gas goes from 8 to 4, it gets cut in half, then the pressure will also go from 8 to 4. And that means that the pressure is going to decrease because 4 is less than 8, so there's going to be a decrease in pressure. And that's why this is your answer. Now think about what could happen if this question were different. Suppose it were about volume with a fixed pressure, and you had a piston with a movable cylinder. Just think about this method of problem solving, setting the ideal gas equation over the ideal gas equation, crossing out things that are constant, which will always be R, and then usually some other things, and then seeing what you're left over with. Question 2. How many grams of, is that sodium chromate or sodium dichromate? I don't know. Let's just call it sodium chromate. Doesn't really matter. With a given molar mass are needed to prepare 0.0450 molar sodium chromate solution with a volume of 100 milliliters. So this is a molarity question. You have to understand that molarity, which is simply concentration, is equal to the moles of the solute, which in this case is the sodium chromate, divided by the volume of the entire solution. And that's why I'm putting L here, because it's typically going to be liters of the entire solution. So when you have this, you're noticing that it asks how many grams of the solute you need. This moles here refers to the solute, but moles and grams are not the same. So do some basic algebra, rearrange this, and see that if you multiply the molarity times the volume in liters, you get the number of moles. Let's plug and chug. The molarity of interest is 0.0450, and the volume in liters is not 100. That is 100 milliliters. So as a little note, remind yourself that 100 milliliters can be converted into liters by remembering that 1 liter is 1,000 milliliters. So you're going to divide by 1,000 basically, and you get 0.100 liters. And that's going to go there. So we have the molarity, we have the volume in liters of the solution, and we are going to do some math to figure out how many moles of the sodium chromate or whatever that thing is. So 0.0450 times 0.1, and you get 0.0045, and that's moles of this stuff. Then, of course, do a molar conversion. So step 1 is to find the number of moles, just being careful that your volume is actually in liters. Once we find the number of moles, step 2 says we're going to do a molar conversion. 0.0045 moles of the Na2Cr2O7 all over 1, and we're just converting that from moles to grams, and we're given the molar mass. So that, remember, the molar mass is a conversion factor that allows you to convert from grams to moles or from moles to grams. So we're going to have 262 grams for every 1 mole, and then you're going to get your answer when you do that. And if we do our answer, we're going to get this number, multiply that by 262, we get 1.179, and with sig figs it's 1.18. Question 3, it says, in Z, the picture shows a balloon with 1 liter of gas. Choose the balloon from A, B, or C that correctly represents the volume of the gas after the external pressure is decreased. So make a little note to yourself that you have pressure decrease by a factor of 4. And the Kelvin temperature is halved at fixed N. So there's a lot to think about in this question. Again, it comes back down to the ideal gas law and using the fact that the ideal gas law really just wraps up all the other gas laws, Boyle, Charles, Amonton/Gay-Lussac's. So let's try it out again. We have P1 V1 is equal to N1 R T1. We put that all over P2 V2 is equal to N2 R T2. As a reference, the ideal gas law is PV equals nRT. Those little 1s and 2s are just referring to the before and the after. This is the before, and then some change happens, and one of these is the after. So one of these represents the 2, and the first one represents the 1. All right, now that you know how to read that, we can get rid of this. Let's see what's constant. So we have to read it again. Usually helps to read it multiple times. In Z, the picture shows a balloon of 1 liter of gas. Choose the balloon that correctly represents the volume of the gas after the pressure changes. So we have a change in volume. We don't quite know which way it's going to go yet, right? Could be bigger or smaller. We'll figure that out. But we know that the pressure decreases by a factor of 4, and the temperature is also going to decrease. And remember, temperature has to be in Kelvin. Now this is a closed container, so a closed balloon, so a container, unless we opened it and closed it, there's no gas leaving. So N and R are both going to be fixed. So the number of moles of gas in the balloon are going to be the same because it's a sealed balloon. R is a constant, so it's also going to be the same. So what you're left over with is P1 V1 over P2 V2 equals T1 over T2. This is one way to write the combined gas law. You could also have moved all the 1s and 2s to the other side if you want to, and you'd get P1 V1 over T1 equals P2 V2 over T2. Just be aware if you're studying and you see it in one of these two forms. They are saying the same thing. Now, we have some information here. We actually know the volume. So you're actually solving for the final... You're looking at which one's going to fit the situation the best. So I'm going to stick with, the top one, since that's the one that you're going to get from using the ideal gas law equation. Move this over here. And here's how you can solve something like this using problem-solving strategies. Replace the initial pressure. Do we know what the initial pressure is? We don't know what the initial pressure is. We just know that the pressure decreased from whatever it was to a fourth of what it was. So if the initial pressure was 1, the final pressure is 0.25. We don't know either of these. This is all relative. So we can put a 1 with the initial pressure. We see the initial volume is 1, so we can put a 1 there. And we know that the final pressure is going to be a fourth of what it was, so we can put 0.25. And we are trying to find V2. V2 is literally what we're looking for, right? Is it going to be a half a liter, the same volume, or 2 liters? So far we have these things filled out. We know the initial pressure was some number, and the initial volume was 1. We know the final pressure was just a quarter of whatever it was, and that's what we did here. It's just a ratio. And we know the final volume is, well, we don't know it. But continuing on though, we know that the initial temperature was some number we don't know, and the final temperature is half of that. So you could technically put 1 for the placeholder temperature. You can put whatever. It says halved, so I'm going to put, doesn't matter what I put at all. It's literally arbitrary. Just to spice it up, I'm going to put 2 for the initial temperature and just 1 for the final temperature. And the reason that I chose 2 and 1 is there is no reason. You could have put a 1 and a 0.5. You could have put 100 and 50. It doesn't matter. We don't know the actual temperature. All we know is that relatively that the initial temperature in Kelvin was turned down by half. So the pressure went down and the temperature went down because it says the temperature Kelvin is halved at fixed N. Halved just means that whatever the temperature was in Kelvin, it was half of that. So any numbers can go there. Same thing with pressure. It's all ratios. All that to say that you're going to use algebra to solve for V2. Now, if you do choose a 2 over a 1, that makes it easy because this entire side over here just becomes 2. Also, the entire top becomes 1. And using some algebra, if I divide both sides by 2 and then multiply both sides by V2, I get 1 over 0.25 times 2 is equal to V2. So 1 over 0.5. And I get 2. So the final volume is equal to 2 liters. So the answer is going to be C. And you can kind of tell here because the pressure on it went down by a factor of 4. So that would tell you that the volume is going to go up by a factor of 4. But it's not going to go up by a factor of 4 because you also have temperature working against it. Temperature decreased. So remember that temperature causes volume to shrink, but pressure causes volume to increase. So if you have two things changing, pressure going down and temperature going down, they're kind of working against each other. Pressure wins though. The decrease of pressure wins over, so to speak, the decrease in temperature, and that's why the volume has a net increase. For number 4, it says, in a gas mixture of neon and argon, the partial pressure of neon is 423 millimeters of mercury. So we can put P subscript Ne, which is the partial pressure of neon, is 423 millimeters of mercury. Keep in mind that this container has a mixture of just those two gases. Then it says the partial pressure, so underline neon here. Then it says the partial pressure of the argon is 312 millimeters of mercury. So we can put P subscript Ar for argon, and that's 312 millimeters of mercury. We are given the mass of neon, and the mass of the neon is 120 grams, but we don't know the mass of the argon. So the main idea with partial pressure is that there are three simple quantities that are going to track with themselves in proportions. We have pressure, volume, and moles. Mass is not going to be proportionate because it depends on the molar mass of the actual gas. But if a container were to be 1/2 the moles of gas A and 1/2 the moles of gas B, that means that the volume of each gas will be half and half, and the pressure of each gas will be half and half. Right now, we can see that the partial pressures are not equal, and we know the molar masses of these two things are not equal as well. So here's the tip to solve this quickly. Whenever you see grams, just turn it into moles, because we know that moles will be proportional to volume and pressure, not necessarily grams. So let's take our 120 grams of neon and convert that from grams to moles. So we'll get rid of grams by putting it in the denominator, put moles of neon at the top. 1 mole of neon, did not give myself very much room here. 1 mole of neon has a mass of 20.18. So the math here says that there are 5.946 moles of neon in this container. Now, what might be very helpful is to find the total pressure. So that's going to be P subscript T. The total pressure is equal to simply the sum of the two partial pressures. So that's going to be 735. I had to do some quick math there. Okay, it wasn't really impressive. But anyways, millimeters of mercury. Okay, so we have the partial pressure and we have the total pressure. It may be helpful, and there's a bunch of ways you can do with this number-wise. You can find the mole fraction. Effectively, you can call it the mole fraction. The percent of each gas. Percentages, are very tightly related to decimal or fractional representation. So once you find the percent or the decimal representation, you can use it however you want. That might be very helpful here. Since we're focusing on argon, we know that this container has less moles of argon than moles of neon. And we know that because it has a lower partial pressure. So since the pressure of the neon the partial pressure of the neon is 423, but the partial pressure of the argon is 312, that ratio is going to help us understand what the mass of this is. So we have the moles of neon, and we have the partial pressure. What would be very helpful for us is to set up a proportion. So let's do that. There are a bunch of ways to do these types of problems. It all comes down to parts over wholes, so just kind of tracking things carefully. In this case, we're just setting up direct proportion. So we know the partial pressure of neon, and we easily figured out the total pressure. So this is some fraction, this is some decimal, and if you wanted to turn it into a percent, you could do that. We also know the moles of neon by turning our grams of neon into moles of neon. So in this method, we're actually going to solve for the total number of moles of gas, and then realize that the total number of moles of gas is going to be equal to the moles of neon plus the moles of argon. So we're going to figure out the total number of moles of gas. To do that, let's do some replacements. The partial pressure of neon is 423 millimeters of mercury. We also figured out the total pressure. The total pressure is 735. Let's put that here, 735 millimeters of mercury. We know, based on our molar conversion, that 120 grams of neon in this container is really just 5.946 moles of neon. So using cross multiplication, you can solve for the total number of moles. So I will do that here. Multiply that number by 735, divide by 423, and we get 10.3325 and something like that. So that means that solving for the total number of moles, there are 10.33, let's call it a 3, rounding. 10.333 total number of moles. I'm going to label that here because that's going to be important to know. Total number of moles. Now this container only has two gases, neon and argon. So if you do some basic math, you can figure out that if there are 10.333 total number of moles and 5.946 of those come from neon, then how much comes from argon? So let's do that. I'm going to shrink this down. We don't really need it too much to give us some space. And what we're going to have here is that the total number of moles is going to be equal to the moles of neon plus the moles of argon. And then basic algebra tells you that you just subtract, right? So we're going to have here is about 10.333 is equal to the 5.946 plus, and then that's going to be what we're figuring out, the moles of argon. So doing some basic subtraction, we're going to have 10.333 subtract away this other number, and I'm keeping the more precise digits in the calculator, and we have this information. The moles of argon, therefore, the moles of argon are going to be equal to 4.386, and as you can probably guess, we need to turn those moles of argon into grams of argon. So to do that, I'm just going to do a molar conversion. This is going to be moles of argon. Moles of argon are going to be turned from moles of argon into grams of argon, using, of course, the molar mass. And the molar mass is 39.95 grams per mole. So I'm simply going to multiply that number by 39.95, and I get 175. And that's how you solve a question like this. Keep in mind that volume is also proportional. So if you were given a total volume, let's say that this problem were extended, and this problem said, and this whole shebang of two gases, the neon and the argon, are all in this 7-liter container, and you were asked to find the volume of argon or the volume of neon. It would be the same thing as we set up with that direct proportion. Parts over wholes equals parts over wholes. You will always know enough to solve for that missing part, whether it's between pressure, volume, or moles. In this question, we didn't care about volume, but if this question had given you a total volume or even a partial volume, you could figure out the rest using that problem-solving strategy. And number 5, in a sample of a nearly ideal gas, this graph could represent a plot of. Here are the main plots that you'll have to, the main relationships you have to recognize. Pressure and volume. Those are inversely related. When pressure goes up, volume goes down. Imagine you have a cylinder with a movable piston. So you have something like this. And it has a movable piston on it. And you have the gas on the inside. Here's your gas. If you were to decrease the height of this piston, so that the height were here, and we're decreasing, just think about the fact that, volume of a cylinder, for example, is equal to pi r squared h, and h and v are directly proportional. So if the height goes down, then the volume goes down. Then you got to think about the ideal gas law, or Boyle's law, and think about when volume goes down, these particles inside are going to be squished together and the pressure is going to go up. So volume and pressure are inversely proportional, so it'll look like this. Now, you also have other relationships such as pressure and temperature. As temperature goes up, pressure goes up. You also have volume and temperature. As temperature goes up, volume goes up. And then you also even can extend it to moles. We don't really need moles in this case. But for example, moles and volume. If you were to add more gas, the volume will increase, assuming other things are constant. So this is just recognize those relationships, and then it'll easily help you figure out which one is which. Any of them could be on this test. In this case, the one that fits is the one that says it's going to be pressure versus volume at constant temperature.